I'm very happy to share my PhD research work, which I have been doing for 4 years. And today I'm going to discuss about the topic of my PhD dissertation is risk-based optimization of design, the case of structural fire design. So I'm going to take roughly 45 minutes for the presentation. First of all, I would like you to walk through these three structural fire events, basically to introduce you the consequences of fire in structures. The first one is Grenfell Tower fire. It's a fire in a multi-story building. It's a 24-story building in UK, and the fire started in fourth floor with fire in freezer, and then it engulfed the whole building. And there was huge loss of life and property. Around 72 people died, and based on the statistics, the property loss amounts to around 1 billion pounds. And the second one is the tunnel fire. So the tunnel is located in Switzerland, and two trucks collided with each other, and there was a huge fire which caused huge damage to the tunnel, and it also caused loss of 11 people, and also the tunnel remained closed for around 2 months after the fire. And the third one is Notre Dame Cathedral fire, which you all know. Most probably, the fire in the cathedral occurred at the roof of the cathedral, and then it destroyed the entire roof almost. So why these three buildings basically? So because these three structures represent different aspects of the consequences of fire damage to structures. The first one shows the damage to life and then property. The second one shows the indirect damage caused. So if the tunnel remained closed for 2 months, you can imagine how big impact it would have on the company, offices, and several other works nearby. And so the indirect cost was huge. And the third one represents the damage to the cultural heritage. So I think the structure, the history dates back to almost 800 years, and it damaged something which has been built very back, and so you can realize the value of the structure. So as explained about the three structures and their damage consequences, the consequences of the structure can be grouped into these 5 consequences, and based on this world fire data for the fire cost, roughly 1% of the GDP of most of the developed country is spent on the cost of fire, the cost for fire protection, and then the cost for this type of damage due to the structure. So realizing we have huge consequences of fire on the structures, and we have huge amount of the fund going to the fire protection of the structure. Our structure should be designed adequately and adequately for the fire, with considering the economic point of view as well. So, but how do we design our structure for fire? So normally we consider prescriptive approach. Prescriptive approach means we have design standards, design guidances such as Euro codes, and these design guidances provides us requirement for fire design. So for example, here let's take an example for a reinforced concrete slab, which is designed based on Euro code 2. And to design this reinforced concrete slab, which has this thickness of HS and axis distance of A, we get the value of these parameters from the Euro code. We have these standard fire resistances for different duration of fire exposure, and correspondingly for one-way slab or for two-way slabs, we have these axis distances. So we just go into the Euro code, we look at the data, and we design our structure. And this is the standard fire curve, which is shown here in the table. But in these situations, we assume that our design is safe and adequate enough. Why so? Because these tabulated data are based on the historical performance of the structures, based on the failures in the past, based on experimental tests, and based on numerical investigations. So in this case, we assume our design is safe. But what about the design for special design situations? Special design situations, which I mean is like now we don't use the standard fire curve, which had only heating phase. Now, if we have a natural fire curve, which have heating phase and cooling phase as well, or we have special type of materials For example, now let's say wooden or timber, or we move to some other advanced materials or high strength materials. For those situations, developing prescriptive designs or design requirements is very difficult because we need huge resources, we need huge time to develop these design requirements. So for this type of design situation, we adopt a performance-based approach. And what is a performance-based approach then? In performance-based design, we are free to choose our design alternatives, our design materials, our design approach, and then we are also allowed to choose our own design objectives. But then the societal design objectives should always meet them. Basically, we need to demonstrate in the performance-based design itself that our design is safe enough. How do we do that? We can do that by explicitly evaluating the safety level. So how do we demonstrate that our design is safe in the performance-based design approach? Then one of the approach is through probabilistic risk assessment. We can plot the risk profile of the structure and check whether our design is safe or not. So for a basic introduction to risk, for fire exposure of the structure, let's say there is a structure and then there is a fire on the structure, and the likelihood of occurrence of fire is lambda. And due to the fire, then there is consequence of the structure, and which is, for example, D. Then risk is defined as a function of the product of this likelihood of fire and the consequences of the fire. So now we know what risk is. But what we can do is we can also plot this risk profile in a plot here. For example, here the plot is shown for general frequency consequence diagram. So here what we can do is we can plot the consequence severity on the horizontal axis, and we can plot the frequency of accidents of these consequences, and we can plot the risk profile on this graph. And if our design lies below this tolerability limit, our design is acceptable. And if it is above this tolerability limit, it is unacceptable. So basically, we ensure our design is either in the LR region or de minimis region. But how do we ensure that our design is there, like in LR region, or is sufficient enough? So one of the approach is through cost optimization. What we can do is we have the investment cost associated with our design alternative, and corresponding to that investment cost, we have risk reduction or risk associated with that structure, and we can explicitly balance these two, and then our design is safe enough, we can say. So now you understand the meaning of the topic of my dissertation, which is risk-based optimization of design. In the case of structural fire design, I defined risk, I defined optimization of design, and then I defined what structural fire design is. My dissertation can be divided into two parts. The first part is methodology and tools. In this part, I develop the methodology for risk-based design frameworks, and then the tools which supports those risk-based design frameworks. And in the second part, I implement those risk-based design frameworks using the case studies. So coming to the first part, I have 3 chapters in the first part. The first one is the risk-based design optimization framework, and the chapter 3 and 4 supports and basically provides the tools for the risk-based design optimizations. So coming to chapter 2, which is framework for risk-based design optimization. First of all, I would like to discuss the first framework, which is the lifetime cost optimization. So I would again discuss the same example for the risk, where I defined the definition of the risk. So first of all, let's say we have a structure, and for that there is a particular design solution or alternative, and the cost associated with it is C1. And corresponding risk, or we can say damage cost associated with the structure, is this one. And then we have another design alternative, C2, and similarly we have another design cost, damage cost, and for the ith cost we get this the ith consequence or the damage cost. And if we plot these investment costs, some of these investment costs and these damage costs in a graph, we can get the optimum point or the data point. So let's see this graph. So what I did is I plot in this orange line this investment cost, which increases with the increase in the value of the design parameter. Let's say if there is only one design parameter, and then the failure cost decreases with the increase in design parameter because the probability of failure decreases. And so if we plot the total cost, which is the lifetime cost, we have an optimum point, and that's how we do lifetime cost optimization here. To generalize more, because this was for the discrete case, so to generalize more, we can formulate it as a lifetime cost, which is the sum of the investment cost and the damage cost here. So this investment cost is the same, which I said here, but it also includes the obsolescence value, which is the cost of degradation for the investment with the year on year. And so since it is a future value, I also used here discounting factor to get the present value of those obsolescence costs. Similarly, the failure cost of the structure, it's just we are at the design stage, and so the failure cost associated here is the future cost, and we convert it into the present value here also with the discounting factor. So this is how we do lifetime cost optimization. I will discuss more of this using case example in later chapters. And now we have this again. Let's focus on this equation for the lifetime cost. We have the first objective for, let's say, investment cost, which needs to be minimized for a design, and then we have this failure cost, which also needs to be minimized. So we have two design objectives here. And we added these two design objectives. But what if we have multiple design objectives and we cannot add up those design objectives? For example, for the environmental cost, the environmental cost is normally measured in CO2 emissions, and it do not immediately have a value of the economical value or monetary value. And so we cannot add up here, and we cannot, and then the optimization becomes difficult. So for those situations, what we can do is we can apply multi-objective optimization approach. And here is a general framework for multi-objective optimization. So in this, based on this framework, what we first do for multi-objective optimization is we formulate a multi-objective optimization problem. What we do is we define design objectives, we define design constants, and we define design variables. All of these can be multiple. And then using an optimizer, for example, here it is genetic algorithm, we get multiple trade-off solutions. So multiple trade-off solutions here means they are also called Pareto optimal solutions, and they actually present optimal surface for the entire design objective. And once we have these multiple trade-off solutions, that is the optimal solutions for the entire design space, based on the higher level information, we can get one best solution. So what higher level information I'm talking about is, for example, if we have environmental cost and we have CO2 emission, which we evaluate, we can assign CO2 emission, a monetary value, which can be a variable. And then for any combination of that CO2 emission to for any combination of the conversion factor, we can immediately evaluate the best solution. So this approach becomes very efficient in that way. And also we are free to choose any number of objectives, because in the other optimization, in the lifetime cost optimization, if we add on the different objectives, we have to perform a grid analysis, and it becomes quickly challenging and difficult. So that's how multi-objective optimization is quite significant. And third framework here, it's not like basically a framework, but I presented it here as a framework just to keep it a bit separate. So it's the generalization of the results of the cost optimization. So the lifetime cost optimization, multi-objective optimization involves a lot of tasks like evaluating the investment cost, evaluating the failure probabilities, evaluating the consequences. And so it's quite laborious task. And then carrying out this optimization for all of the projects we have, it becomes very challenging. And so what we can do is we can propose a common target, and based on that target, we can design our structure. That's how we can avoid the entire cost optimization approach by just looking at that target. So this is already followed for normal design condition, not for fire. So this is already followed in normal design condition, for example, in JCSS and ISO standards, where they propose these target reliabilities for the design. So what target reliabilities means, from our cost optimization, which we see, we get an optimum value of the design parameter. And for that optimum value of the design parameter, we can evaluate, there is a corresponding probability of failure, which we can call as optimum failure probability. And then there is a corresponding target reliability, optimum reliability, which we can select as target reliability. So for common design situations, like if we need to establish common design standard, we can adopt this approach and propose these target reliabilities for that. In order to validate the approach, I carried out this lifetime cost optimization. For normal design condition, I plotted the different lifetime costs here in function of the center safety factor for normal design condition, and then I got the optimum value of the design parameters, and corresponding to this, I got the target reliabilities. And this is just to check if our approach is in line with the current state of art. And we compared the obtained target reliabilities with the standard, that is JCSS, and we can see that the target reliabilities match well with what is in the existing standard. But for the fire design, we don't have these target reliabilities defined yet. So basically, our design standards do not provide anything such as target reliabilities for our standard. So one of the tasks for my PhD is also evaluating these target reliabilities for fire design based on this cost optimization approach. So now, now I'm going to discuss about the tools which have been used in my dissertation to support this cost optimization. The first tool is surrogate model-based structural fire design optimization. So let's see again the lifetime cost optimization equation. So we have this lifetime cost. For the evaluation of damage cost, which is a risk-based, we have to evaluate the failure probability. And this is also a function of the design parameter and also the fire scenarios. So evaluating this failure probability is quite computationally expensive. So if you see this flow chart here, for the failure probability evaluation, we need to run our structural fire analysis 10 to the power 4 times. And structural fire analysis is itself a computationally expensive task, because you need to first carry out thermal analysis, and then you need to carry out the structural analysis. So it is a two-step process, and if you adopt a finite element approach, then it quickly gets too expensive. So for that, I propose surrogate modeling approach, and then our task for evaluating this failure probability or probabilistic analysis becomes easier and computationally efficient. So what do we do in this approach? We replace these SFE models with the ML models, which are also called surrogate models. And how we do this? We train this SFE models with this machine learning models, and then we directly use it for our failure probability evaluation. So as a case study, I consider two application examples here. The first application example here is a case where bending moment capacity of slab is evaluated, and this bending moment capacity of the slab is evaluated based on this equation, which also gives bending moment capacity for fire situation. But for fire situation, we need to evaluate the temperature of the rebars in the slab. So it is although an analytical equation which requires no computational expense, but evaluation of temperature requires some computational expense. So it is a little computational expensive as well. Yeah. So in order to make surrogate model for it, I considered regression-based surrogate model. For example, it's a 2-degree polynomial here, but other degrees polynomial also has been checked, and the best one has been fitted. So it's not shown here exactly because it's a big model, and so the probabilistic analysis is carried out for this slab, and you can see the probabilistic distribution for the bending moment capacity of the slab in this graph, where we can compare the probabilistic distribution from the actual model and surrogate model. And the surrogate model, one of them is based on just 100 samples. That is, the surrogate model here is trained only for 100 sample data. And for the other case, the surrogate model is trained for 2000 sample data. And for the 2001, it performs quite well. And surrogate model with 100 is also quite close. So this shows that surrogate model approach can be used for the probabilistic analysis, and it results in quite a bit of accuracy as well, and it reduces computational expense significantly. So as a second application example, a bit complex structure is taken, that is a bit of computationally expensive structure. So as a second example, the case of an RC column is taken for which the load capacity, axial load carrying capacity is evaluated, and it is done in a finite element program, which is a field. And for that, to evaluate 10,000 evaluation for the probabilistic evaluation, we need around 7 days of calculation in a standard PC if we use one core. And when we use surrogate model, it becomes quickly cheaper, and we can also evaluate it for the lot number of combination of the design parameters. So here also you can see the comparison of the probabilistic distribution, which is the cumulative density function here, the comparison of the CDF between the actual and surrogate model, and it also matches quite well, especially at the lower quantiles here. So now the next thing which we required for our lifetime cost optimization is fire damage cost. And for that, in this chapter, I propose the damage cost evaluation framework. So if you see here in the lifetime cost equation, we need another factor here, which is the failure cost factor. Failure cost factor here basically is the total cost of damage in a structure divided by the cost of the compartment. And so that's how failure cost factor I have proposed here. It becomes easier when we use these type of factors to define our failure cost. Our optimization becomes easier, and we can do a lot of parametric analysis. And this failure cost, that is the total damage cost in the structure, includes the direct cost and also the indirect cost. The direct cost includes the property and property damage cost, and also the human fatalities and so on. And indirect cost is basically used here as a percentage, but in real life problem, we can include this business interruption cost, financial loss cost, and others in these factors as well. For now, it is just considered as a factor, this indirect cost in this study. And two application examples are shown here to show how damage costs are evaluated. The first one is a direct evaluation of the damage cost. What we do is we apply fire on a structure, we evaluate the damage, and based on that damage, we evaluate the cost to repair it or the cost to replace it if there is a need. And the second one is a risk-based evaluation of the fire cost. So what in this, we list out all the consequences associated with the structure, and also we calculate the likelihoods of those consequences, and then we get the final total cost, and it's a risk-based. I will discuss more in detail. So for the first application example, I considered a case of a composite slab panel. So this is a structural model of composite slab panel. We have concrete slab, which is resting on this steel beam, and we have the reinforcement in the concrete slab. The figure on the right shows the numerical model for this structural model, and which is simulated now with the boundary beams, which has two girder beams, two boundary beams, and two central beams, and all of these structure is exposed to fire. And two design situations are considered to evaluate the damage cost associated with the structure. The first case is the prescriptive design, and the second case is the performance-based design. So in prescriptive design, we protect all the boundary beams and also the central beams. But for the performance-based design, we protect only the boundary beams, and the central beams are not protected. So protection here I refer to is spray applied concrete material protection on the steel beams. And so here for the performance-based design, we do not apply those type of protection, and we only apply at the boundaries. But our design, however, when we check for the standard fire rating, which has only the heating curve, both of these designs, even when these are unprotected, shows the same fire rating almost. Both of them shows a fire rating of around 1 hour and 15 minutes. And for the simulation of the fire, we don't consider here standard fire curve. Normally in design standard, we consider standard fire curve, which is the heating phase which is the time, I mean temperature curve with the time, and it always it increases in this fashion. For my dissertation, I mostly consider natural fire curve, which is Eurocode parametric fire curve, which has the heating phase and the cooling phase as well. And this is parametric fire curve is considered as a function of fire load density, how much fuel load we have, and the opening factor. What is our opening or ventilation condition in our compartment? So this is how the parametric fire curve is defined in the rest of my dissertation. And how do we estimate the damage to the structure once the structure is exposed to fire? That is, when the composite slab panel is exposed to fire, we evaluate damage as the damage depth in concrete. So if we have a concrete slab, there is fire in the concrete slab, we evaluate the depth inside the concrete slab up to which the temperature of 300 degrees centigrade is reached, and those parts needs to be removed and replaced with the fresh concrete. And that's how that damage is evaluated. And then the another parameter to evaluate the damage is the deformations. What is the deflection in the concrete slab? And for the steel beams, we have the damage is measured through the damaged SFRM layer. So basically, we evaluate the temperature because at 300 degrees Celsius, the SFRM damages quite heavily. So if it reaches more than that, we consider our SFRM is damaged. And another parameter is for the steel beam, which is the mechanical parameter, is the heat straightening parameter. We check whether our steel beams can be repaired by heat straightening or not. So once we have these damage measures for the composite slab panel, we can associate a damage state. Basically, we define whether it can be repaired or not. And if it is repairable, we estimate the repair cost. And if it is not repairable, we take the value to replace the structure entirely. And this slide shows the repair costs or damage costs evaluated for our two design situations, the prescriptive design and performance-based design. And we saw before that these two design cases have almost same fire rating, but but here we can see that the repair costs are different for these two cases. So for the prescriptive design, we have lower repair costs for the lower fire severity. However, for the performance-based design, most of the cases are irreparable because there is huge deformations in case of the performance-based design in complete slab, and due to which most of the cases of the slab panel is irreparable. And so basically what we here achieved, that is we achieve is the cost saving insulation, but this is not very efficient when we see it from repair cost point of view. So although we try to save this cost on insulation, but from repair point of view, it is the cost saving is not efficient because we have huge cost in the performance based design. So the next application example is the steel column in a multi-story building, and the steel column is exposed to fire here, and it's a 9-story building, and it is an office building. And in this case, we evaluate the damage cost based on the risk assessment. And for that, these are the 4 consequences considered, which are repairable and irreparable condition, and if there is a failure of the compartment or the failure of the entire structure. So basically, if the steel column is exposed to fire, then either it do not fail or it fails. And if it do not fail, if it is either repairable or irreparable, and if it fails, then there is just the failure of the compartment or the failure of the entire structure. So based on these consequences, we evaluate our damage costs. And for the evaluation of the likelihood of the repairable case, the failure case, and for the failure of the compartment itself or the entire structure, we consider these factors. So for the failure probability, we consider the exceedance of the buckling capacity. So if the buckling capacity is exceeded, we evaluate the failure probability of the structure, and if it fails, we have the cost of the compartment associated with it, and so on. So now this figure shows the present value of the total fire cost evaluated for the structure, and we can see that R30 performs best. R30 has the lowest lifetime cost and is therefore best design alternative for that column. Here, basically, I forgot to tell, we took 4 cases of the fire protection on the steel column. Unprotected case, R30, R60, and R90, and here R30 performs best. And then based on those total fire cost, we also evaluate the failure cost factor. Here, the failure cost factor is evaluated in function of the robustness of the building. That is, if the compartment fails, then whether the entire structure fails or not. We consider this based on the probability of robustness of the building, and this is plotted here in x-axis. And we also compare the total failure cost of the structure with this for this failure cost factor. So failure cost factor is defined here in function of the total cost factor and then the robustness factor. And this total cost factor comprises of the direct cost, indirect cost, and the fatalities. So for our reference column, the failure cost factor is obtained as 207 times the cost of the compartment. So basically, it is 0.61 times the cost of our nine-story building. So if there is fire in the building, in our reference building, the fire damage cost is 0.61 times. For our optimization, I'm going to consider this value for the next application example. So now coming to implementation, the implementation is carried out in 3 chapters. The first chapter is lifetime cost optimization. The second one is multi-objective optimization, and the third one is system level effects consideration. So basically the same application case of the composite slab panel which we discussed before. Let's first see lifetime cost optimization and the evaluation of target reliabilities. And as an application example, the same case of the steel column is considered because we already evaluated the failure cost factor there. And the failure and the probability of failure is again evaluated based on the exceedance of the buckling capacity. And you can see the failure probability evaluated for the steel column. Here, the optimization parameter for the steel column is the thickness of this protection material. And so the probability of failure here is evaluated in function of this insulation thickness and also in function of the fire exposure parameters. Fire exposure parameters, I mean, is the fuel load, as I said before, and the ventilation conditions. So once we have our failure probability evaluated, we can plug in these in the lifetime cost equation, and we also have the failure cost factor here, and the investment cost here is the cost of the increased value of the thicknesses of the insulation. So that's how we get the lifetime cost, and we can obtain the optimum value of the lifetime cost based on this. And here the red curve shows the plot of these lifetime costs, and we can see that that for the reference steel column, which is the fire exposure for office building standard is 420 megajoule per meter square, and for that case we have an optimum insulation thickness value of 17 mm if we consider our ventilation factor of 0.04. And this figure here shows the insulation thickness evaluated for in function of the fire load density for the different fire load density and for the different ventilation factor. And corresponding to this, I also plot here the different fire ratings here for those different insulation thicknesses. And for our office building, which has the fire load density of 420, we can see that R60 is sufficient for all the ventilation condition. So R60, which is 1 hour of fire rating, is sufficient for this type of building. And here now I show once we have this optimum value of the insulation thickness evaluated, we have the corresponding target reliabilities. And so here I plot these target reliabilities for in function of the fire load density and also the opening factor and another parameter, which is the failure consequences. Now I'm changing the failure cost factor as a variable, and then you can see the results for different failure consequences. And once we have these target reliabilities evaluated, we can easily design our structure by considering these target reliabilities. And these target reliabilities can indeed be part of design standards. After we can generalize this target reliability in design standards. For our reference case, when we considered without the sprinkler system and fire rescue service, the target reliabilities obtained was 2.9. But when we considered the sprinkler system and the fire rescue service, basically what happens when we consider the sprinkler system and fire rescue service in the building, the probability of fire decreases, and so the target reliabilities also decreases. So it decreases to 1.1 when we consider the active fire protection system in our building. The same is done for another application example, the case of the reinforced concrete slab. And for here, for the reinforced concrete slab, I optimize this reinforcement axis. And this figure shows the optimum insulation thickness in function of fire load density and the opening factor like before. I'm just showing these results, and here you can see the standard fire rating associated with these optimum reinforcement axis. And for our case of reinforced concrete slab, which is a residential building, we have a fire load of 780, and for a fire load of 780, the R90 fire rating here is sufficient for all ventilation conditions. Similarly, we evaluate the target reliabilities, and we also got this target reliability for the reference case is 3.0 and 1.1, quite close to the value before. So if we evaluate these target reliabilities for this type of standard design situation, which is going to be most often repeated in the future, then we can propose these target reliabilities, and then we don't need to carry out the cost optimization entirely. And then we are moving to the next chapter, which is the multi-objective optimization. So in this case, we introduce additional design objectives, for example, minimization of the investment cost, and we also introduce additional design variables. So the same application example of the reinforced concrete slab is considered, but in the previous lifetime cost optimization implementation, I only considered the reinforcement axis as a variable, but here now I'm going to consider the reinforcement area also as a variable, and you can see the influence of considering these two variables. The bending moment capacity of slab varies quite significantly considering these two variables. For other variables, this bending moment capacity did not vary significantly, so those were not considered. Only these two design variables were considered. And here, additional objective was considered, which is the lifetime, which is the environmental cost. So we had this lifetime cost in our lifetime cost optimization approach, but then we also consider environmental cost. But if you look closely to these design objectives, we have these two parameters: the increased reinforcement area and the probability of failure, only the function of the design parameter and the fire exposure. So why do we need to consider the entire terms here? We don't need. So what we can do is we can simplify our implementation by considering this increased reinforcement area and failure probability separately as an intermediate design objective. And we developed this Pareto optimal front, which I showed in the general framework for multi-objective optimization, where these are actually those Pareto optimal front for our design application case. And once we have this Pareto optimal front for our intermediate design objectives, we can plot them back into these equations, and we can get the Pareto optimal front for the real objectives. So this is how it is performed here. And I consider two cases. The first case is the case where lifetime cost and environmental cost both are considered as design objective, and the normal design conditions, that is the target reliabilities for normal design, is considered as design constant. And how these two are combined or minimized is the lifetime cost is added to the environmental cost by considering a conversion factor for CO2 emission to dollars. And then we plug it into the values for the environmental cost and lifetime cost here to obtain the optimum value. And this figure shows the optimum value of the reinforcement area and reinforcement axis for our case, and it is also in function of the fire load density and these conversion factors. So we see that this blue line shows for the case where only lifetime cost optimization is considered as design objective, because term is considered 0 here. So basically this returns back, this terms goes, and this is the same standard case which was done in the previous chapter. And when we considered the increased value of this conversion factor, we see that the requirement for the design parameters reduces. This is because the contribution of in the environmental cost from the reinforcement is significant, while the contribution from the failure of the structure is not so significant. And that's why there is a decrease in the reinforcement area here. So we can conclude that the design parameter reduces with the increased conversion factor value, the monetary conversion factor value. In the second case, the lifetime cost is considered as design objective, and the post-fire repairability is considered as a design constant. And for this case, we can see that post-fire repairability governs our design decisions for failure cost factor of 200, But when we use the failure cost factor very high, for example, 1,000, then our cost optimization comes into action. But for the lower criteria, our post-fire repairability governs the design, because the post-fire repairability makes our design parameters so high that our failure cost becomes so low, and that's why the optimization do not play any role until this failure cost factor of 100. And yeah. So with this, I conclude the multi-objective optimization. We discussed the two cases for the multi-objective optimization. First one was with the environmental cost consideration, and the second one with the post-fire repairability consideration. So in this chapter, I investigate the system level design optimization. So as a case study, I consider the same case of the composite slab panel. So we have here the 4 steel beams and the concrete slab interacting with each other, making it a system level action. So we consider the same application example here to demonstrate that. But here we didn't consider the two design scenario there as we considered in the last chapter. We considered here four design situations. The first one is the central beams here. They were unprotected. If you remember, in the performance-based design, and the boundary beams were all protected in case of the prescriptive design, and the central beams were also protected in prescriptive design. But here what we do is we vary this insulation thickness for these central beams, and we actually try to optimize the insulation thickness for central beams. And that's how we do lifetime cost optimization for these 4 cases. And we see that for all of these 4 cases, we have almost a same value of the standard fire stance rating, which is 2 hours of fire rating. However, these two design situations have different failure modes. The first 3 modes goes into the tensile membrane action sooner or later. What happens in this case is these steel beams, which are unprotected, with the occurrence of the fire, the system loses this steel beams, and so our slab panel then goes into tensile membrane action, where the reinforcement in the slab takes up the maximum force and the maximum tensile force, and the concrete at the periphery, they takes up the compressive force. And so the failure here occurs by the failure of the boundary beams. But in case of the R120 central beams, which is the same level of protection as the boundary beams, only this middle portion takes off the major tensile force, and so we have a huge forces in these girders, and the failure occurs by the failure of these girder beams. And that's how the failure mode is different in these 3 cases than this case. And here we can see the failure probability plot for these 3-4 cases, and we plug in these failure probabilities and the costs in this lifetime costs, and we have these 2 plots, 2 graphs showing the different lifetime costs for the different fire load densities. The first one is for the case of 420, which is for the office building, and the second one is for the residential building, which is 780. And we can see that for the lower fire load densities, we have these the unprotected case performs better, because we don't have a huge failure cost associated. But with the increase in this fire load density, we have an increased failure probability, and so the failure cost increases significantly. So in this case, R90 performs better. So now I'm going to show these lifetime costs plotted for in function of the fire load densities. That was just as a summary for the 2 cases, but here we can compare for the different fire load densities, and we can see a change here at this point, and higher than this point we have R90 performs better. Then we have higher fire failure costs, and while for the lower fire intensity, there's lower fire cost, and that's why unprotected case performs better. So basically for designs, in our case, for the design which even has same ISO fire rating, lifetime cost significantly different for the natural fire exposure with these different fire load densities. So let's come to conclusion now. So in my study, I first proposed a novel risk-based design framework, the multi-objective optimization framework, where we can input multiple design objectives, multiple design constants, and multiple design variables, and it is quite efficient computationally as well. And then I proposed surrogate modeling for the probabilistic analysis. So using surrogate model, we can reduce our computational expense significantly. And in the chapter with the fire damage cost evaluation, we saw that the overall cost saving in insulation from performance-based design is not efficient when we see it from repair cost point of view, because from repair cost point of view, they were very high in case of performance-based design. And in the implementation part, we saw target reliabilities evaluated for the different application examples, and we can include these target reliabilities in our design provisions so that we don't need to carry out our risk-based design or cost optimization completely. And we saw that the consideration of the environmental cost reduces the requirement of the design parameter. And finally, we saw how system level and the lifetime cost optimization influences our design decisions in case of the case study of the composite slab panel. With this, I conclude my presentation, and thank you all for the attention.